So, welcome to Science Intellect Hub. My name is Mr. Mojakisane, sir. They call me Mr. Mfanabo. So, halala right now. So we are continuing our journey, of course, of talking about functions. And in today's session, we want to ensure that we talk about what we call mother graphs. Now we'll find out exactly what are mother graphs. Recall that in our previous session we have defined as to what exactly is a function. And one of the things that we said about a function is the fact that a function is a relationship. Okay, that's fine. A relationship between two variables. So that is why we are going to have the Cartesian plane to work with most of the time. Because we will be looking at two variables. One, the x-axis, which is horizontal. The other, y-axis, which is vertical. So we say a function is a relationship between two variables such that each value of the independent variable. Remember that we said that the independent variable, of course, will be our input variables. So each value of the independent variable corresponds to exactly one value of the dependent variable. That is what we said, meaning each input value must be reliable. Press 1 plus 1 in the calculator, it must give you 2. Press it again, it must give you 2. Imagine you press it again and it gives you 4. Holy shit, that's impossible. That's no longer a function. So now when it comes to functions, remember we said we have different ways of representing a function. We can use words to represent a function. We can use tables or numerical values to represent a function. We can use equations and even graphs to represent an equation. And I said we are going to focus a lot on equations and graphs. This is what is going to happen. For instance, you are going to be given a function y is equals to x plus 1. And recall that we said now Remasepa blind. Instead of saying y, we could instead say something like, okay, f of x. How about that? Because now we are using what we call function notation. So f of x is equals maybe 2x plus 1. That is the equation of the function. How then could we represent it as a function? Well, as we said, it is a representation of what? It is a representation of two variables, or it is a relationship between two variables. For instance, if this is my Cartesian plane with the horizontal x-axis, the vertical y-axis, well, we can have something of this nature. So we've taken an equation such as f of x is equals 2x, and we've represented it that way to say, well, that is how it may look graphically. Now, here is our concern, here is our interest in Fanabo. So look at what is happening. There is one x value, there is one y value. So each input value corresponds to exactly one output value. There is my input, there is my output. There is my input, there is my output. There is my input, there is my output. Kanjalo, kanjalo. What we see from this function is that each input value corresponds to exactly one output value. So, right now, we are getting real now with functions. Let's discuss what we call mother graphs. We have to understand what we call parent graphs. Weirdly, functions, just like us human beings, just like animals, they have parents. That's weird, but that's a reality. So now, what we have in front of us is what we call the family of parent graphs. The first one that we have here will be what we call a linear graph. Then the other that we have will be what we call a parabolic graph, an exponential, as well as what? As well as a hyperbola. We'll go through each and every one of those, of course, individually. For now, we just want to understand some of the basic things about each and every graph. Most of the time, specifically for linear functions as well as parabolic functions, what we'll recognize is that if we are talking about parent graphs or mother graphs, they usually pass through a point called the origin. Remember, the origin is a point whereby, of course, the axis intersects one another. It is where the axis crosses one another. I'm talking about the y-axis as well as the x-axis. They cross one another at a point called the origin, and it is a point of 0, 0, meaning the x is 0, the y is 0. That is the case for both a linear as well as a parabolic function. But look at the mother graph of an exponential function. Look at how it looks. It looks very beautiful. This is what we will call a exponential function. In terms of graphically representing a hyperbola, of course it may look weird and shit like that, but nothing scary with a hyperbola. So now so we have a mission when it comes to functions. It matters not what kind of function are you talking of and about. Be it is a linear function, be it is a parabolic function, an exponential function, a hyperbola, or even what we call trigonometric functions. We have to know the basic shape of each and every function. So we have to ensure that we know the basic shape of each and every function. Check. Look at how a linear function look compared to how a parabolic function look. A linear function, of course, is a straight line. Whereas when it comes to a parabolic function, look at how a parabolic function looks. A parabolic function will either be a smile or a sad face. Something like that. So, halala. Right now, look at that smile. It's beautiful. It's a good day to smile. So now, when it comes to also exponential and even hyperbolic, along with trigonometric functions, we have to know what is the shape. Check. Are you able to determine the domain and the range of each and every function? I wonder. Check. But each and every function, each and every graph will require you to be able to determine the domain of that function. What is a domain? I wonder. Do you know that? The domain is the set of all input variables. Check. And also the range then being the set of all the dependent variables. The set of all the output variables will be what we call the range. So we are moving at 120 kilometers per hour. Blind. We must be able to determine the domain of each and every function. So they will ask you to determine the range. Are you able to determine the range? I wonder. So we must be able to do that. Now, when it comes to functions, there are these important points which we call intercepts. They get crucial by the year. They get crucial as you go. So at grade 10 level, most of the time they will only require you to determine the x-intercept, to determine the y-intercept. But really, what are intercepts? Well, intercepts could be where axis crosses one another. For example, where the y-axis crosses the x-axis is what we call the origin. And of course, that is also an intercept. Maybe an intercept as well could be where, of course, the graph or the function itself crosses the intercepts. For example, when you look at this exponential function, we can see there is the function. We can see there is a point of intersection there at a01, where, of course, the graph itself is crossing the y-intercept. So we can have y-intercepts, we can have x-intercepts for functions. Are you able to determine such? Yes, booze. Intercepts. Check. But also, when it comes to intercepts, as we go on in grade 11 and 12, we will recognize that we will not only be interested in the x-intercept, y-intercept, we may also be interested in where, of course, graphs themselves crosses one another. For example, we may have 2 or even 3 maybe functions or graphs in the same Cartesian plane, and where one graph cuts another, where one function cuts another, that's also an intercept. So right now, well, other graphs have what we call intercepts, or rather have what we call turning points, specifically graphs like the parabolic function, they have what we call a turning point. Graphs like the sine function, cosine function, which we'll discuss later when we talk about trigonometric functions, they have what we call turning points, whereas other functions have what we call asymptotes. So, halala. Right now we are moving at 120 kilometers per hour, Remasiba blind. So other functions then will have what we call asymptotes. Siyamfuna kodwa simtholi. Remember, an asymptote is that point in the graph whereby the graph approaches, yes, but it never reaches, ever. It never ever reaches that point. That is an asymptote. Turning points and asymptotes, check. Now the most important part when it comes to functions will be transformations. What we have here in front of us is mother graphs. Guess what is going to happen? As we get deeper into the study of functions, we are going to perform transformations based off these mother graphs. For instance, look at what I have here. F of x is equals x. That is my mother graph for a linear function. If I transform it, I may have something like that. I've transformed it like that. I've shifted it somehow. So transformations could be things such as shifts, things such as reflections, and stuff like that. So, halala. Right now. So when it comes to each and every function, we must be able to determine the shape. Check. We must be able to determine the domain and range. Check. We must be able to determine intercepts. Check. We must be able to determine turning points, if any. Determine asymptotes, if any. Check. Most importantly, for each and every function, we must be able to understand the effect of what we call A, the effect of what we call Q, because that is going to be part of what we call transformations. Halala, right now. Foundation is laid. It's time to move on. It is a lesson that you will learn the hard way in real life. To move on. I don't know from what, but some of the things is just naturally hard to move on from. So I'm happy with the fact that we've laid the foundation of what functions are. And we're going to take a deeper look, of course, at what we call linear functions, explicitly and implicitly, in the next session. I hope you found value in this video, and if you did, please ensure to like, comment, but most importantly, subscribe. Gimahala. Welcome to Science Intellect Hub. Till we meet again. Peace.